Hi, I'm Charles Poynton, and welcome to FX PhD Fast Forward class, Introduction to Digital Color Theory. You might think that the two words introduction and theory are contradictory, but what I'm going to do is try to strike a balance between those two to lay the foundations underneath the color science that we use to do color image coding in HD, digital cinema, VFX, CGI. Now, my friends at FX PhD thought that I would be qualified to teach this course, partially because they've already seen me teach the theory at a higher level in the DCT 301, 302, and 303 courses. But another reason is they know I wrote this book, Digital Video in HD, Algorithms and Interfaces. And like we somewhat carefully chose the title for this class, I chose the title of this book very carefully. The title includes the words algorithms and interfaces. And if those words are scary for you, you may not enjoy the book. Now, the book contains a lot of mathematics verging on electronics, physics, optics that lurks behind HD. And much of the color science material in the book is applicable to digital cinema as well. But for today's course, we are going to be less mathematical and more conceptual. And if you need to learn more of the theory in any particular topic, of course, I welcome you to dig into the book. We'll start by an extremely simple slide which simply shows you the way that an image in HD, digital video, digital cinema, digital stills, computer graphics, digital photography, all of those arenas start with a rectangular image carved up into rows and columns, which I call image rows and image columns. And at each intersection is obviously a picture element or a pixel. And for purposes of grayscale, you could record simply one number at each location. And that number may have more or less precision. In other words, wider or narrower bit depth. We'll discuss those details later. But to convey color, we do so almost always using three components, and you'll learn in today's class that those are typically some combination of red, green, and blue. So typically a pixel has three color components, and so we can talk about sample bit depth of one of those components, which might for commodity desktop computer graphics be 8 bits. And because there's three components to represent color, then in desktop computer graphics, according to sRGB, you would typically have three 8-bit components totaling 24 bits per pixel. Now, we'll go from there to a very broad overall diagram that I use to show the context of digital imaging in the world that most of us live in, HD, digital cinema, VFX, CGI. So my context diagram is this one. And the goal here is to give you just the overall landscape of the whole arena, but now I'm not covering digital still photography or other or medical imaging or other application areas. Here we're focused basically on HD, digital cinema, and to some extent, consumer electronics. So my idea here is to divide that whole large space into three tiers, basically at different quality levels. Really high quality, pretty high quality, and let's call it somewhat lower quality. And I'm calling those digital cinema, HD, and consumer electronics, abbreviated CE. Now, on the x-axis of this diagram, I'm trying to show you the flow of image information from production into post-production and finally into presentation. So let's start with the digital cinema level, where production refers to what's taking place in the studio or on the set, basically capturing or acquisition of images. Those images are then handed over to the post-production process, which in cinema is more commonly called digital intermediate. And at some stage after the images are manipulated and composited and had VFX done and CGI, at some point those images are polished up and approved. And that happens on a special reference or approval display. And the imagery is then locked down for launching into the distribution pipeline. And I'm not showing that distribution pipeline, but you could add that tag here if you wish to these lines. And in the case of cinema, presentation of cinema on the ultimate screen is what in cinema is called exhibition. Now, the reason I'm giving you this overall block diagram is that different color encoding systems, if you like different color science, happens at cinema level. And you'll learn later in the course that cinema level is characterized by a set of colors called P3. That is, that's the standard that's used today. And we'll make some reference to emergent standards later. Now, at HD level, you capture with an HD camera, record HD. HD also has post-production. HD, after you've finished post-production, editing, and so on, is then also approved and then mastered for launch into the distribution pipeline. However, there's really no professional level, wide-scale exhibition of native studio quality HD material. Instead, usually what happens is we launch HD into the distribution channel, which really ends up in the hand of consumers and is viewed in consumer displays. So I'm sort of level shifting to one level down the pipeline here. Now, it is possible to acquire image information using consumer equipment, in which case there's typically no post-production. The consumers might edit, but they rarely do anything more sophisticated than that. And so they view their own material on consumer displays. But I'm leaving out this block diagram of the chart, or saying that there's negligible post-production, so we'll enclose that box in dotted lines. Now, the professional level HD presentation I've enclosed in dotted lines. However, I can think of one example of material which is absolutely high-level studio quality, which is then launched into a distribution chain at HD studio levels. And that's the project originated by my friend Mark Shubin, HD from the Met Opera. So in essence, this is a live HD production taking place in an opera house, which is then distributed using HD distribution technology to various cities in the world where people view it in cinemas. However, HD is characterized by a color space called 709. And so when the HD from the Met material is exhibited to viewers around the world in cinemas, those cinema projectors are dialed into the 709 color space instead of the P3 color space typical of cinema. Now, down here at consumer level, the color space is very similar to 709, but it's called sRGB. And the parameters are slightly different. You'll hear the details later. Now, one other issue that takes place between digital cinema mastering and distribution is that when movies or other high-end pieces of material are mastered in P3 space, but typically movies, but for business reasons it's desired to distribute those, well, historically DVD, today maybe Blu-ray, or increasingly across the net with Netflix or Apple iTunes Store or other IP distribution technologies. Typically what's done is the movie will be mastered in P3. That P3 master is exhibited in the cinema, but that image data material comes back through what I call a trim pass to have its color parameters adjusted to have that material put into the 709 space for distribution using standard 709 HD terminology. So that's my overall block diagram of the whole landscape. And all of these presentation technologies involve mixing R, G, and B components. But in front of the camera, what the camera sees is really spectral information that has not been separated out into RGB. So now let's go and talk about how spectrum maps to different colors. And then later on, we'll talk about how those different colors are mixed. So here we are in the lab, demonstrating separation of white light into all the colors using a slide projector, which was quite some trouble to locate, a narrow aperture in the image plane, which we constructed on the fly, and a prism, which is located about 6 meters back in order to produce enough dispersion. So the prism that we're using is one exactly like this, and it's located half a meter from the slide projector. So you can see what's happening is that the white light is dispersed by the prism and presents this rainbow on our white wall. You can see that we've got red, orange, yellow, green, blue, and these are the colors that Isaac Newton talked about when he finally, 30 years later, wrote this experiment up in his book. But he didn't stop with ROYGB. He went I and V, indigo and violet, because you can see that there's quite a range of blue colors portrayed. And in a few moments, we'll turn off the lights on me and you'll get a better sense of the colors that are displayed. And you get some notion from this diagram that yellow seems to be a unique color, although you can see here we're blending it across from red to yellow to green. But yellow, as I mentioned earlier, is a perceptually unique color by virtue of the way our visual system is wired up. Now, the other thing I'd like you to notice from this real rainbow experiment is no purple, because you go out into very deep and very intense blues, but there's really no color there that's got any combination of long wave and short wave, and it's those combinations with not much or nothing in the middle that creates the visual sensation of purple that's absent from the rainbow, because all of these colors have got a peak just at one wavelength. They've only got one lump in the spectrum. So let's now switch our lighting off to give you a better notion of the colors up in the blue range of the spectrum. So here's the spectrum without being interfered with lighting. And there's a couple of features that I'd like to point out to you. You can see that the brightest portion of the spectrum is in this range. In terms of physics, the power distribution is roughly the same all the way up and down the whole rainbow, but the visual sensation is brightest around here, and that corresponds to around 550 nanometers. And down here, there is light below the red. That's, of course, infrared. And eventually, well, in our particular light source that we're using in this experiment, there's really no ultraviolet to speak of. But when Newton did this experiment, he did so using sunlight. So he would have been refracting infrared light as well as ultraviolet light, but we can't see that. And you may notice then this ROY, Roy G. Biv, blue, indigo, violet. You're getting quite intense colors up here, but none of them can really be described as purple. The other little detail of Newton's sketch that I love is his use of a second prism lying behind the card. He's cut a little hole into the card, put a prism behind that, And because I have a second prism here in my hand, I can show you that phenomenon. He's showing you that once the light has been separated by the first prism, no further separation is possible. So here, if I had a wideband light source incident on my second prism, I'd display the whole rainbow. But because the light has already been separated into its fundamental components, there's no separation. I just repeat the same color. This is a real color science course, so we're going to show you real color mixture using a set of 3 spotlights: red, green, and blue. And I think you can imagine that if you start with green and add blue, basically we've got medium wave light. We're going to add short wave light, and you end up with light having short wave, medium wave, and no long wave. That mixture appears cyan. You might call it turquoise. Now, if we eliminate the medium wave light, start with short wave and add long wave, short wave and long wave mixed together with not much in the middle gives magenta or purple. And both of those mixtures are quite intuitive. The troublemaking mixture is the next one coming up. If we have long wave light and you mix that with medium wave light, you get yellow. And it's not at all intuitive that that mixture would be yellow, because for perceptual reasons, the way our visual system is wired up, we treat yellow as a unique color, and we don't easily, or maybe at all, see yellow as a combination of red and green. In other words, we have colors which are bluish green, and we have colors which are reddish blue or bluish red, purple, but we don't have any notion visually of a greenish red or a reddish green. In fact, physically though, the mixture is yellow. And of course, if you mix all 3 components together, you get white. That's additive mixture. So you've seen how a particular red, a particular green, and a particular blue can be mixed to form a wide range of colors. And in a display device for HD or for digital cinema, we'll perform mixtures like that at each pixel. And that concept maps back into our original diagram from the top of this section of the class, having the image matrix and each pixel element split into 3 components. Now, you do have to beware that there's different color standards where the red, for example, in digital cinema, 100% pure red, is a little different than 100% pure red in HD. So later on in the course, we'll talk about different RGB systems for different applications. But for our purposes today, just be aware of that. Now, another thing that you have to be aware of is that certain cameras and certain displays don't have this straightforward concept of a pixel comprising 3 individual components. This is normally the way that we think of images in the middle of the system, but the way those images come in from a camera or the way they go out to a display might be different depending on the camera and display technologies in use. Now, perhaps the best way to do image acquisition and image display is to think of a way that we could construct physically and electronically a camera that would take the shortwave component of the spectrum coming in, make that blue, the medium wave component, make it green, the long wave component, make it red, but have all of those components perfectly superimposed on the image matrix like I've shown in this diagram. And that scheme can be done if the camera involves an optical assembly that splits off the short waves, splits off the long waves, and takes the medium waves and imposes each of those three wavelength bands on three separate sensors. That's the way color acquisition was done in video for the first 50 years of color video, using what's called a prism or a beam splitter camera, or also a 3CCD camera or 3-sensor camera. But that prism is big and bulky and heavy. So it became common, well, it became feasible about 10 years ago and common about 5 years ago to have a single sensor upon which little filter elements are overlaid, RGB, 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 or maybe even RGGB, RGGB, RGGB. And so the image matrix comprises all of those color components mixed up together. So I've explained that ideally, from a theoretical point of view, the best way to do both acquisition and display would be what I call, and one of the words in the title of the course is theory, so I get to use theoretical words, optical superposition. So the red, the green, and the blue are laid right on top of each other. So there's some sort of optical separation at the camera and some sort of optical recombination at the display. Now, I've explained that you could use a beam splitter to separate those components at the camera. You can also use a beam combiner, which is basically exactly a beam splitter, just the light going the opposite direction. So red, green, and blue goes into this prism assembly, and the combined beam comes out. Exactly that scheme is used in digital cinema projectors, also known as 3DLP. If you're using the particular DLP technology from Texas Instruments and its manufacturing partners, that's exactly what happens. So the beam on its way to the digital cinema screen has already got the red, the green, and the blue already optically combined together in the same beam. And so when they reflect off the screen, those pixels have got individual red, green, blue components. But another way to do it is to build a display which has got individual red, green, blue emitters, or potentially even red, green, green, blue emitters, and make those little emitters so small and so far away from your eye that you can't individually see those dots. What you see is just the average of those added together by the time they go through the optical system of your eye and get imaged on the retina of your eyeball. So this scheme is called spatial multiplexing, and it depends upon having those elements so small that you can't see them. And the same concept is used in cameras. You build one imaging array and put little filters in front of the individual sensing elements, typically RGGB. And that particular scheme was invented by a research scientist at Kodak 35 years ago. His name is Bruce Bayer. And this scheme became known in cameras as the Bayer mosaic. Now, in order to take that information and turn it into this information, somehow you've got to have some signal processing or algorithm or software that takes that RGGB, which are located spatially at slightly different positions, and merge them together somehow into three color components that are now spatially coincident. So we're used to doing all of the processing downstream with those color components in register. In a camera, that operation is called demosaicing. So demosaicing involves, you could have RGGB forming an image with the same pixel structure, but now 3 times as many samples, because each of the locations has now got an R, a G, and a B, where previously it was an R, a G, or a B. So demosaicing, say, from a let's say 4K by 2K camera, so-called 4K camera, it's got 8 million little pieces of light, or 8 million total color components, but mosaicked in this RGB structure. And if you then demosaic to 4K, you got 24 million little pieces of light, or 24 million total color components. So you might be asking yourself, where did those 16 million additional pieces of information come from? And the answer is, they didn't come from anywhere. They were just guessed or estimated by the demosaicing algorithm. So you have to be very careful when you talk about a 4K image from a camera or a 4K image that's presented to a projector. And typically a 4K digital cinema projector will be using this structure where there are in fact 3 components for each of those 8 million pixels. So 4K in a camera means something conceptually quite different than 4K in a display device. So in the case of HD, we've got basically 2000 by 1000, well, technically 1920 by 1080, but let's call it 2K by 1K times 3, or 6 million little pieces of light, where a so-called 4K camera is only delivering you 8 million little pieces of light. So the two are actually quite comparable in performance. All of this depends upon having red, green, blue components, and the focus of the rest of the course will really be on what are those 3 color components, and will be in the rest of the course mostly independent of the pixel structure, independent of how the camera captured the image, independent of how the display device displayed the image. So we'll be based on this image matrix structure. We'll be talking in great detail about all of the different sorts of color components that are used to represent images. So in today's class, we've talked about RGB, that being the kind of canonical generic image processing color format, but there's many, many other color formats, many of which I'm sure you've heard of. So there's YCbCr, very commonly used in HD, common in the distribution scenario. There's XYZ, used for digital cinema mastering. Also XYZ used for color science. There's LAB, available in Photoshop. There's HSV and HSL, used in color grading. Many different kinds of color coding systems, all of which use 3 components. And in future classes, we'll talk about the transforms among all those different components.